All right, let's have another look at the identity that we wanted. We wanted log of a times b to be equal to log of a plus log of b. It's not. At least it's not always true. So let's see how we can figure out what's really true with these unwinding numbers. What is true about a is it's equal to e to the log a. So e to the log a is always a, although log of e to the a is not always a. We get to go this way. That's right. That's okay. Phew, at least we get one thing. B is e to the log b. That's again a valid thing. When we multiply exponentials, we get to add the exponents. That was part of the exponential function. Exponential is nicer than log. We get to do that. So therefore, e to the log a times e to the log b is e to the log a plus log b. Log of e to the anything is the anything minus 2 pi I times the unwinding number of the anything. So this is what's true. If this unwinding number is 0, for example, if a and b are both positive real numbers, then the imaginary part of log a is 0 and the imaginary part of log b is 0. So the imaginary part of the sum is 0. We plug that into our ceiling formula for the unwinding number. We get 0 minus pi over 2 pi. That's minus 1/2. We take the ceiling of that. We get 0, and that term drops away. So if a and b are positive, log of a times b is log of a plus log of b, as usual. Plus there's some freedom in there. There's some other situations where this thing turns out to be 0. There's a non-trivial clear-cut region for this. Great, but we're fundamentally just using this relationship, that the log of e to the z is z minus 2 pi I times the unwinding number of z. So let's have a look at another rule from the real value of the logarithm. We know, well, we want log of a to the power b to be b times the log of a. Not true. The definition of a to the power b for complex powers b is exactly this, e to the b times log a, where the log is as defined before, so it has this property. So log of e to the b times log a, well, log of e to the anything is the anything minus 2 pi I times the unwinding number of the anything. So that's what's true. It's not true that it's just b times log a unless this unwinding number is 0. Sometimes we get to show that the unwinding number really is 0 for all z. So let's look at the square root of z, log of square root of z. Well, that's the log of z to the 1/2. All right, that's e to the 1/2 log z. So we get 1/2 log z minus 2 pi I times the unwinding number of 1/2 log z. And it turns out that the unwinding number of 1/2 log z is always 0. And that's because the imaginary part of logarithm is trapped between minus pi and pi. So if you take 1/2 of that imaginary part, it's trapped between pi over 2 and minus pi over 2. And so the ceiling of that divided by 2 pi is somewhere trapped between, sorry, we've got to subtract pi. So it's going to be minus 3/2, pardon me, minus 1/2 to 1/2 of this, pardon me. Let's work it out in detail. Pi over 2 minus pi is minus pi over 2. And the ceiling of that is going to be 0. See, I've got to divide by 2 pi, sorry. 2 pi. Ceiling divided by 2 pi is the ceiling of minus 1/4. And at the lower limit, it's also true. Pi over 2, pardon me, minus pi over 2 minus pi, can't do that, I'm at minus 3/2 pi divided by 2/2 minus 3/4. So the ceiling of minus 3/4 is again 0, and so this number is always 0. So the clear-cut region for the square root function is the whole complex plane, and so the log of square root of z is always 1/2 log of z. This turns out to be 0, always. So sometimes we get to keep the familiar rules, but sometimes we don't. As an exercise, I would ask you to do the case when b is -1. And so z to the power -1. And you'll see that it's almost always true that log of z to the power -1 is minus log of z, but there is one place in the complex plane where this unwinding number is not 0 for b equal -1. Thank you.